After learning information about the basic gates, now let us learn about the different types of combinational and the sequential circuits. Basically, all the digital system designs, they are being classified into two types of circuits. One is combinational circuit and another one is the sequential circuit. So the basic difference between these two circuits are any combinational logic design, it will not have the feedback path, and the output of these combinational circuits doesn't depend upon the output of the previous state. But in case of a sequential circuit, there will be a closed path or a feedback path from the output to the input, where the output of these sequential circuits, it depends on the output of the previous operation on that particular circuit. So these combinational circuits without this feedback network are operated in most of the cases and for all the real-time applications. Basically, the three basic gates which we studied in the earlier section, they can be used to implement these combinational network, to implement any of the given algebraic function which is used to implement the real-time applications. So once we get the knowledge about the basic gates and the combinational logic, this can be implemented for all the implementations of algebraic networks. For example, before going to the actual implementation, let us learn about some of the laws and identities in the logic design unit. So firstly, the one of the basic theorem which we have for this conversion is called as De Morgan's theorem. So basically this De Morgan's theorem is defined as the complement of any function, it is equal to the complement of the individual terms. For example, here you can see in the slide the example number 1, we are complementing an AND function, means A and B, they are multiplied and it is complemented. According to this De Morgan law definition, it is equal to the complement of individual functions. For example, A is a function, this dot is also a function, and again this P is a function. So according to this De Morgan's law, this A is complemented as A bar, and the complement of this dot is nothing but OR function. That is, dot is called as the AND function. The complement of AND function, that is the inverse of AND function, is OR function. And again one more term we have is B, which is being complemented and it is represented as B bar. So here we can see the symbolic representation of this conversion of De Morgan's law. Here A into B means two outputs, they are being ANDed and it is being complemented, which is represented by this bubble, which is equal to the individual complements which are being ORed using or added using an OR gate, and the respective output is nothing but the inversion or the conversion which is of this function, which is done by De Morgan's law. Similarly, you can check the De Morgan's law in rest of the three examples, which are nothing but A plus B whole bar, which is equal to the complementation of individual functions, and this OR function is being complemented to AND function. Similarly, this A plus B, it is being complemented through this De Morgan law. All the individual resultants and the input terminals, they are being represented by the symbolic representation as shown in the figure. So next we shall move on to the actual implementation of a given logic expression using different types of the gate. So for this example purpose, let us consider implementing the given expression using an AND gate. For example, first let us take the first logic expression, which is equal to, which represents z equal to x bar plus y bar plus z bar. So before going into the implementation, we have to simplify the given expression by applying the De Morgan's law. So the De Morgan's law is nothing but the complementation of the given function. So this given function is being complemented, and resultant is nothing but x dot y bar dot z whole complement. So this is the resultant of the given algebraic function, and this logic expression is being represented by, or it is implemented using only NAND gates, which is as shown in the figure. So similarly, by applying De Morgan's law, any number of given logic expressions, they can be simplified to its simplest level, and then they can be implemented using any of the basic gates, like we have considered the NAND gate. So similarly, you can use NOR gate or XOR gate to implement any of the given logic expression.